Hello, everyone. Hi. I welcome you all. This is the objectives and what are the basic things that I will be walking you through today. We will have an overview of what exactly big data is and how RDBMS has comes up with the limitations when we are talking about a very high volume of data in there. And then what exactly NoSQL comes up. Before I believe, it's very important that if we are actually jumping into Cassandra, so it's very important that we have a brief understanding of what exactly NoSQL is and what was the real need of coming up with NoSQL and what are the specifications of a NoSQL, how we represent or how we define that this is actually a part of the NoSQL stack now. And then the CAP theorem. Now, once you guys have an understanding of NoSQL, the basic principle of how NoSQL works is primarily on the CAP theorem, the consistency, availability, and partitioning. So these are the three basic pillars on which every NoSQL works primarily, and then which of these three features are being extensively used in Cassandra, and how Cassandra actually behaves or responds to these three features, and what exactly CAP theorem says. That's something that we will have a look in today. And then probably we can have a brief overview on Cassandra, what is the kind of structures and what are the basic features that Cassandra gives us. And then I will walk you through the installation of Cassandra. Primarily for installing Cassandra, what we have done in Edureka is we have made the life a little more easier and simpler. We have a set of installation documents that have an existing virtual machine completely set up with the required set of softwares already in place. You just need to download that specific virtual machine and install it probably in any of your VirtualBox or virtual players. Anyways, I will walk you through when we reach that point of time. So until then, let's keep going. Once the objective, that is the primary objective. Let's suppose, if we have a conventional store, if we understand how a conventional RDBMS works. In a conventional RDBMS, we always have various sets of data stores, and then those data stores we primarily refer to as the databases. And then inside the databases, it's primarily a very structured. We have various kinds of relationships. We will have tables in there, and then those tables will be linked to each other or probably within. And then probably we will have various unique identifiers that define those relationships, probably based on the keys. Well, that's a primary key, unique key, or any other form of key. And then we will have those relationships based on those keys, primarily maybe a foreign key or a unique key that defines relationship between one or two multiple different tables. And then based on that, but the basic key concept in every RDBMS is that we always know what is the kind of structure, what is the kind of information, and what is the exact format of data that we actually are going to store in a specific storage structure. That's always a very basic prerequisite in any RDBMS implementation, whether that goes on from a MySQL store or to an Oracle server. For example, let's suppose that we have an e-commerce application and there is one of the features is retail. And in case retail, we have products. So probably there will be a products table for say, and then products will have a unique identifier, probably a product ID, and then probably it will have a product name and stuff and so on and so on. But the most important thing in there is as soon as we actually define the structure in there, we primarily don't change the structure that extensively. Obviously, we can change the table at any point of time, but it's very difficult, especially when we have different relationships. First of all, you have to define a unique identifier, probably it's mostly the product ID in there. Then we have to define the type of that ID. Then same applies to the name that we have specified in there. Probably it is, for example, let's suppose in case of name, it might be a string. So that's a varchar in there. And then if it has any other attribute, probably description, then it will have varchar or text specified based on what kind of store we're using. But in every form of an RDBMS, we're always very certain that what kind of data will exactly store in there. So the structure of the table primarily does not change. It's mostly fixed and it's mostly stringent. That is something when we actually have very high volume of data, and as soon now, since the structure or the behavior of the applications, the interactions have changed a lot now. Now, in case of an RDBMS, We always know that the data is always identified in the form of rows and the specifications of the identifiers for those rows are columns, and the combination of columns and rows represents a table that is a unique identifier for a specific set of rows and columns. And then probably we can always have multiple number of rows and multiple number of columns, and those columns are probably just like in our case, just like the example I gave you for the product. So probably product is a table wherein there might be various different columns. There might be product ID, there might be product name and product description. And then probably the values in there will be the rows identified in there. And the rows is the actual data that represents the more valuable information inside that storage. But yes, I mean, a conventional RDBMS is more optimal in a transactional storage. It extensively and it acutely supports the ACID, the atomicity, the consistency, the data definitions. Most of the basic principles of managing the data is extensively, it's very enhanced. But the biggest drawback with any RDBMS is its robustness, its scaling up. Scaling up of an RDBMS is always very complicated and challenging because there's a very different memory model that an RDBMS plays, and every table has a specific set of logs, and then there are different transactional management systems, the distributions, and the operations, how it writes to the actual database files in the backend internally. It's a very complicated process, and it's always time consuming and tedious. And when we have high volume of data, it's always very time consuming for any RDBMS to actually specify the structures that need to be written to files. And now, since as I told you that a conventional possible storage, since there's no limitation, there's no specific expectation what we will be expecting now. When I say it with respect to the data that we are actually interacting with, or the data that we are actually talking with. Now, the expectations have changed now with the diversification of the information technology or the data management or the data interactions. Now, the kinds of systems have grown up. There are various possibilities. There was a time where we always knew the data would always be in a specific structure, or then we had the concept of semi-structures. There were specific patterns, or there were the specific formats in which the data would be actually specified. Then we have the unstructured one. Now, since the data has actually grown extensively, the industry is actually becoming more stable and stable now. So things are changing now, and the possibility of the structure of data is relatively majorly getting unidentified now because since we always want to make our systems more robust and more optimal and acceptable to change, then susceptible to failure. So it's always very possible that there is no specific structure of the data that we will have a predefined one or in the prerequisites. So there's a possibility that data might not have any specific structure in place. So there's a possibility that we might want to store the complete files in one go, or there's a possibility that we might not store all the files in one go, probably one specific section of a file at once. And probably as we move on, the structure of the file might keep on evolving or might keep on changing as we progress or as the system grows on. So that is why it makes more sense to ensure that we're able to manage, or we're able to ensure that we have that consistency in managing, or we have the acceptance, or we have that leverage to manage that kind of store wherein we don't have a very well-defined or very predefined structure for managing that very high volume of data, or those unstructured or unexpected formats of data. And as we see, if you see, this is the possibility of the graphs now. As we are going ahead, as we are moving up over the period of times now the amount of unstructured data is actually going on. The amount of unstructured data is getting more as compared to the amount of structured data, because since as I told you that everyone wants to be very robust and very flexible, so we cannot have a very confined or a very, very stringent set of structured data inputs or data items that we'll play around with. So I mean, that's why the volume of unstructured data moves on. And now, as soon as the unstructured data moves on, it's always being identified as the one specific term. That's what we identify or what we represent as the big data environment in place, in picture. So, I mean, even though primarily in big data, there will always be a high volume of data, regardless of what structure is, what structure exactly, what is the structure of the data. There might be a possible structure or there might not be a possible structure. However, the major or the biggest chunk of big data stack is always the unstructured structure, since the volume of unstructured structure is more and it's scaling up. It's extensively accelerating. I mean, if you see in the past few years, past 5 or 6 years, the volume of data is going in exabytes. That's what the predictions say. I mean, as per the predictions, probably by 2020, we might have actually reached of approximately around 4 zettabytes of unstructured store. That's a huge amount of data. And once we have that much amount of data, it's always very important that we have places or we have stores who are always very who are there to support or who are there to manage those unstructured items or unstructured sets. And that's what big data actually comprises of. I mean, since when we have very high volume of data, we don't necessarily know that how we will be processing. So the processing or the manipulation or utilizing the data is always very complicated and very complex, because now, since this is not something a conventional store, so there is no specific set of predefined rules, or there's no specific mechanism to process that data or to get more something more informative out of that data. And if you see, especially if we talk about the social media, the possibility of the data can always vary. You can have someone, for example, if you go in Facebook or any social media app, the possibility of the data will always vary. There might be a person who probably is pushing, probably uploading tens or thousands of posts on Facebook every minute or second, or then there are people, and the structure of that post can always vary. There might be a video, there might be an audio, there might be a picture, there might be a text, or there might be a combination of a text or a picture. There might be a combination of a text or a video. So the possible structure of the store or the data is actually it varies. And same applies to, I mean, or for example, if you see something like Instagram, where people are always Instagram or YouTube, wherein there are extensive amount of heavy data objects or heavy data items, probably like images or videos, but people keep on uploading them extensively, probably per second. I mean, if you see per hours, there are probably hundreds or thousands of videos that everyone keeps on uploading per second. So the amount of data is actually growing on. The amount of data is actually really not changing. And the structure of the data, there is no specific format. There is no specific structure of data in there. And for a conventional RDBMS, it's almost near to impossible to manage this much amount of data, because considering the transactional structure or transactional behavior of any RDBMS, so amount of time RDBMS actually requires to process or to write or to perform various conversions for any specific data formats, it's almost near to impossible for any RDBMS to take a look at that and do the corresponding writes within that data stored server. Now, for big data, there's 5 V's, or what I call as the 5 basic V5s, the V5 engine, how I refer to it as. That's what the big data primarily talks about, whether the amounts, the volume, how big data is actually growing, how the amount of data put in to the store, or how much amount of data needs to be processed extensively is always very high. So the volume, that's what the volume actually talks about, because since in big data, it's always about volume. It's always about very big volume. But that can be a historical or real time. That's always different. Then the variety. Now, since primarily big data is mostly talking about the unstructured stores, so we never necessarily really know that how exactly are the data actually, how or what kind of data will be preserving in there. So there's always various possibilities that the structure of the data will always vary. There might be a possibility that someone might be only sending about structures, probably JSONs or objects. There might be someone else who might be just sending Word files. There might be someone else who is just uploading, who's only talking about PDFs. There might be someone who's only talking about movie files. There might be someone who's only talking about the audio files, or there might be any other possibility. So the structure, the possible forms of data is always very varied. It's very diversified. That's what variety talks about. And the velocity. Now, since we have an extensive amount of volume, so that means there might be terabytes of data that is actually being pushed in, or that needs to be managed. That's where we talk about the amount of data that's actually already there. Now, how the data is actually being put into here. So that means there might be trillions of records that are coming in to the store, or there are zillions of records from various different kinds of possible locations that are actually being pumped in, or that are being sent to a different or specific a data store. That's what the velocity talks about, and that velocity is always going up. Now, since the amount of systems keep on growing, I mean, if, for example, if we just take an example of Facebook, there was a time then where probably there were 100 on probably a 10 million, or then it moved on to 100 million users, then to 200, and so on. And there was a time, and right now it's almost around 1 billion users, 1 billion odd users. And imagine that if everyone keeps on sending, keeps on posting at least once a day, imagine how much data is actually being sent, or what is the velocity at which the data is actually being sent to Facebook, and how much of data needs to be processed, and how much of data needs to be preserved in there. Now, that is what the velocity actually talks about. Now, since I told you that this is the unstructured data, so we exactly don't know what is the exact possible way of processing this data. So there's always a possibility that we might have a lot of useful information in there. Now, the important thing is how exactly we identify that, how optimally we decide that, or how smartly we choose the best or the key elements or the key items from a single data set or multiple data set or across a complete data store that we have. And we have now, imagine that we have terabytes of data, and that terabytes of data is not just fixed. It keeps on adding. It keeps on piling up, since it has an extensive amount of velocity. So there's always someone who's always pushing more data into that specific store. So that means the amount of data always keeps growing up. And now, since it's growing up, so it's very important that we don't just store the data for fun. We always store data to get some specific value, to get some useful information out of it. That's what the value talks out. So it's very important that we always identify, or we always try to leverage the maximum out of the data that we have in hand right now. That's a very important thing. And that is where big data makes more sense. That's why you see a broad stack of tools, and that's why big data has been growing up. That's why there have been always a lot of extensive amount of revisions and so many smart tools that help us in actually identifying what is the amount of data, or what is the optimal usage of data that's already there or that's present there. That's what makes value very important. Then comes the veracity. Veracity is primarily, I mean, of to ensure that, since we know that there's always possibility when we actually are when we have a lot of unstructured storage. So since there is no concept of transactions in a high volume store, we don't primarily expect the management of transactions. So there's always possibility that we might have the same element multiple times, or there's a possibility that we might lose a lot of data, or there's possibility that there will be a lot of loopholes, or there's a possibility that there's a lot of inconsistency in data. For example, let's suppose if we are actually if we talk about a system who keeps on sending his status primarily every second, and let's suppose we have tens or thousands of those machines. Now, since the structure of every machine might be different, probably a machine might be as small as probably a small microprocessor, or as big as a ship. Now, the structure of every machine is different. Now, what primarily we do is we only have a single data store that's preserving all the information that we are getting from all the machines across the world. Now, the amount of data that we get in there it's huge, it's humongous, right? because we can have thousands or millions of small microprocessors, and we can have thousands or millions of those big ships. And the amount of data items or data packets they send, they will be huge. There will be huge amount of data. Now, what happens is, now every time the data is actually being sent, there's always a possibility. Now, since when you're sending high volume of data, there's a possibility that some of the elements from the data get lost while they were being received, while they were being consumed, or suddenly, due to any of the reasons, probably connection failure, network, wireless, internet, any other possibility, or probably that machine going down at that point of time, you lose some information. And while that was being consumed by the consumer at that specific place, who's actually, or that specific subsystem or application who's actually interacting with that machine, failed off to consume some of the data. So that means we were not able to receive all the data from that machine, right? So that is where you will get the inconsistency in the data in there. And then, I mean, the biggest challenge is we exactly don't know what are the various possibilities for those inconsistencies. There are a lot of possibilities now, since it's always a directly proportional thing when we talk about the kind of devices that we can have. Now, since there can be always n number of possibilities for any possibilities in the inconsistency in the data, especially when we are communicating. So that's what the 5 V's of big data primarily talk about. So the volume, the amount of data that we have, the variety, the kinds, the various flavors of data that we have, the velocity, that means the throughput that we have for that data, the value, what is the sensible data, what makes sense and what doesn't make sense, and the veracity, that means probably the inconsistency that we're actually getting in the data store. That's what we are actually primarily talking about. Now, see, from data, since I told you that there is no unstructured, means, I mean, there is no specific structure, so there's no possibility. We don't primarily know whether we are getting a string, we are getting an int. We don't know. We're getting an object. Maybe we're getting an string right now, but tomorrow we're getting an object in there. Right now we're getting a video. Tomorrow we might get an audio in there. So the structure, there's no specific possibilities, right? So now there are the possibilities. There can be various sources for big data, right? So I mean, there's no specific source, or there's no specific producer for various kinds of data, or a huge amount of unstructured data. There's no specific store. But primarily, I mean, if we look around, we can have various kinds of stores. I mean, I would say YouTube is a very logical example, because considering now, when we say the amount of data that we're actually sending in, YouTube actually does a lot of processing extensively in a specific set of time. So it always makes sense to give it to loop it in case when we are talking about the big data stores. Now, I told you that we are moving on. We are doing a transition from a conventional RDBMS to a NoSQL store. So, but it's very important that what are the key components of RDBMS that made us choose a new store? Because why couldn't we optimize something within the RDBMS that we actually really feel? So that's why it's very important first to understand that what we have in hand, and what is the possibility, what is the possible things where exactly this breaks off. Now, I mean, the primary challenge with an RDBMS is we cannot store unstructured, we cannot have an unstructured persistence with an RDBMS. We always need the data to be very well defined, and the structure, the consistency of the data is very important. Then the scaling of RDBMS servers is always very difficult, because the managing the toppling of various servers, it gets very costly, and it's very difficult, and there's a specific limitation of every RDBMS. If we talk about MySQL or Oracle, so the amount of data that we can store even within a specific cluster, and the amount of connections it will be able to open up, or the amount of connections it will be able to handle within a second, is again very limited. So there's always specific limitations on scalability. Then in case of the RDBMS, the distributed cache, so I mean, providing the extensive reads, that's always very difficult. I mean, primarily, I mean, yes, in case of Oracle, yes, Oracle provides few features, but other than that, any other stores, any other RDBM store that we have in there, they don't primarily help us out to solve in that problem. Then the biggest challenge with any RDBMS is cost. It's always very expensive. RDBMS gets very, very costly. So that is always a big challenge in there. So that's something that always confines us off to ensure that we try to part ways when we are talking about putting huge amount of data, a large volume of data within the RDBMS. The managing of that data, that's always very difficult. And then when we have huge amount of data packet that are actually coming in, that we're trying to write, we've always seen that there are always the down performance challenges with any RDBMS, even if that is an Oracle store, and we have huge amount of write that we're actually trying to do. With RDBMS, it's always a big challenge. It always takes a lot of time and a lot of performance, and a lot of memory utilization actually goes on dedicated towards that area. So that actually impacts the overall performance of that specific cluster for that RDBMS store. Then with sharding is always, if we talk about the partitioning and sharding, that's not that extensively very good. That's not very smart because the biggest problem with RDBMS is that it's a relational store. So there's always a lot of relations defined in here. So managing sharding in there when we have high volume of data, that's always, yes, I mean, I don't say that sharding is not possible in there. Yes, every RDBMS store actually provides a lot of good features in sharding, but until a certain extent or until a certain amount of data, as soon as the amount of data actually goes on, it becomes very, very difficult to actually manage those. And especially when we have complex relationships that are actually identified in there. Let's suppose there is a user is linked to a company has a lot of different products, and those products have different set of clients, and then those clients probably might have their own users as well. So there's a tree change relationship that's actually being identified in there. Now, if we actually want to shard the data at a specific user or a specific company, it becomes very difficult because the amount of joins that the server actually has to pick it up from, so becomes it's very tedious and time consuming. But when we talk about big data, the amount of data will be huge. So the number of companies in there might be thousands. And then if we cross multiply those companies with the end users of their clients, it gets very high. So managing those things is always a big challenge with RDBMS. And if we try to split this data across multiple nodes within the servers, within that specific cluster, and then if we actually want to retrieve the data, and then when the actual server actually tries to retrieve the data from those multiple nodes and accumulate all that data, it's never at the best performance in there. But if we try to do a similar thing from an unstructured store, it's always very amazing. It's always very smart. You will get an amazingly extensive performance. Now, this is a sample use case wherein we actually trying to talk about what was the possibilities, what were the problems, and that one of the organizations actually failed to perform optimally when they were actually trying to do a similar amount of high volume data within an RDBMS structured store. The data size, the amount of data was actually growing on extensively. So now the amount of data actually growing on extensively, and the managing of that extensive amount of data within any RDBMS is always a big challenge in itself. And then in order to have fast reads, in order to have very rapid reads, going on to the database, doing a database connection, interacting with the data store, it's always considered a very, very heavy operation for a reason, because it keeps the channel open and it's always time consuming. Now, when you have millions of users in there and who always want to retrieve a specific kind of data that specifies only their needs, so you cannot put you will not be able to put high volume of that data. You cannot keep on sending those requests to retrieve that data at a rapid rate from an RDBM store. That's always a big challenge, and I assume that a similar problem was faced in this use case. And then you cannot keep on adding nodes You cannot keep on adding new instances within the cluster. It's first of all, it's very expensive. Second, managing and monitoring those servers, those individual instances, that's always very difficult and very complicated with RDBMSs. And then if one of the nodes actually got lost, it takes a lot of time for the alternate node to actually go on and relive himself and make that data sync within it, and give his information to the remaining other nodes in that cluster. The syncing of a new node is always very time consuming and very complicated. And then if we have a high volume of writes, if there's an extensive amount of writes as compared to reads, that's again always that's another big challenge that comes with this use case, wherein you have high volume of writes. Billions of users actually are trying to write their information or write their data simultaneously at the same amount of time. I believe these are the possible issues that Insight faced at that point of time. So now the probabilities, see, I mean, there are always possibilities that we will come up with. I mean, there are always very possibilities that we can come up with solutions to suffice our needs. But now our needs can vary. Now, if we consider the same use case that we just saw on our previous slide, now as per them, they have a set of things that they actually require, that they actually exist, or that they actually expect to exist in the store that they are actually trying to, wherein they are trying to preserve their data store. One is the scalability. It should always be very scalable. It should be very easy to scale up or scale down. Then it should not run out of memory. So that means it should always be able to scale his memory up, and it should always be very easy to enhance the memory of the data store. Then the availability, it should be, it should never be down. It should ensure that now, since when you have millions of users, you cannot expect a downtime. It's always very important that you should be able to manage a very high availability. Then sharding, and then, I mean, spreading the data across multiple nodes and ensuring that the partitioning has been done automatically, or the partitioning is being done optimally. That's the another feature that comes in the expected list. Then fault tolerance. I mean, let's suppose if there was a feature, if one of the nodes actually got down. So what is the solution, or what is the alternate way of solving that problem of how to overcome that issue without giving a downtime for the system or the cluster. And then sharding shouldn't create problems. So I told you that there are a lot of complications that actually come across, especially when you have huge volumes of data, and when the interconnections in between those data items are huge. It's always very complex, and it's always very time consuming for the clusters to actually perform the sharding. So to ensure that those complexities are reduced, that's another expectation. And then obviously everyone wants to make sure that everyone wants that you build an optimal system at the minimal possible cost. It's always cost effective. Then the processing, the most important feature is, I mean, when we are actually interacting with the data, whether we are writing data or we are reading data, it's always very fast. So it doesn't take much time on the processing side. That's always very important. Now, what exactly, I mean, as an RDBMS, it's very obvious that these things are not relatively the forte of a conventional RDBMS. That is what a NoSQL store, that's where a NoSQL store actually comes in picture, and that's what NoSQL actually helps us out with. Now, with a conventional NoSQL or a conventional unstructured store, now the first thing is that there is no specific structure that needs to be followed. So the expectation, the possibility is that the data that we're actually preserving in an unstructured data store can always change. Now, so there is no specific expectation on the schema side. So we don't need to predefine the schema for any conventional store. So the structure can always change. It can always grow up or grow down. Now, since it's schema less, so that means there is no concept of relationships. So there won't be any relationships between various set of data objects. So it's very important when we're actually working with NoSQLs, we ensure that we are very smart enough to manage those relations alternatively. As we move ahead, I will explain how we can actually do that, how we can do a transition from a conventional relational store to a NoSQL store, and how we can handle those relations, how and where we can handle those relationships. And then, the elasticity, of growing up or growing down of the various nodes within a cluster, and the concept of sharding, how to define or how to devise, how to spread the data across multiple shards automatically without actually doing a lot of custom operations or custom management. That's always a very helpful feature that we're expecting. And then always the distributed environment, the distributed management of, because now since the basic feature of the NoSQL, the basic expectation of the NoSQL was to manage a high volume of data. So it's very, very important that now, since a high volume of data cannot be managed by one single machine, so that means it's always expected that there will be always a group or multiple set of machines, bunch of machines that are working together within a specific ecosystem that we represent as a cluster. So that is what the distributed environment comes in picture, to ensure that a one single source is actually spread across multiple machines, so that it gives an effective performance in place. And then the scalability. So there's a possibility that we might be working on, we might deploy our servers on Amazon right now, and then probably we might do a transition on Google Cloud or Azure, for say. So the transition is always relatively simple, and then it should always be scalable. So we should always be able to enhance the performance, probably whether that's the enhancing the performance vertically or horizontally. So that means adding more nodes to the same cluster without affecting the health of the existing cluster, or scaling up in a way wherein the amount of if the velocity of the data is actually increased, whether that's the in velocity or the out velocity, regardless of that, the cluster is smart enough to handle that much amount of load. That's always a smart thing. And then a seamless integration with the in-memory stores. For whether we talk about the temp persistent stores or the caching, what we identify is, or reducing the amount of expectations for leveraging the caching features. So giving more optimal performance, wherein we don't primarily require much of caching features. These are the basic expectations, or these are the basic features that we expect in every NoSQL. Now, there are various structures. There are various possible NoSQLs. The structure of how they store the data, how they structure the data, that always varies. There might be a key value store like a map. There might be a store that stores data in the form of documents. There might be a column-based store, or there might be a graph store. And then every store has all the NoSQL stores always have a unique identifier, that is the index key, or the specific key that actually identifies, that gives the information on how the data is actually being spread across a node or multiple nodes. And the information about the information of how we can grow up, that differs, that depends. There are some stores who are optimum on the write side, then there are stores who are optimum on the read side, then there are stores who are optimum on both, who have a balance on both the things. Then there are stores who are optimum in managing relationships, then there are stores who are more optimum in managing the unstructured source. So it depends on the expectations and the needs, and the amount or the kind of data that we try to preserve, to understand. So it's very important that first of all we should understand, and we should be very well aware about our needs and expectations before actually choosing before actually choosing a data store for our needs or for our implementations. It's not it cannot be random. It should not be a random choice, because there are a lot of stores. There's React, there's DynamoDB, there's Redis, there's MongoDB, there's Elasticsearch, there's Cassandra. Then there's Neo4j, there's Orient, there's Titan. There's a lot of data stores that exist in the industry right now. For example, in a key value storage, the key is primarily the unique identifiers, and then the values actually specifies in here. So based on the key, so I mean it's similar to a map. The performance, I mean, how exactly, see, the optimum way of actually storing the data in here is, one way is we actually store all the data on one single node. But the challenge with that is now since right now we have only three values in here, but now let's suppose if we are getting 300,000 of those values per second, so the amount of that the amount of data that we're actually trying to preserve in one single store is extensive, is humongous. So what we do is we don't necessarily store all the data on one single node. We spread it across multiple nodes within the same cluster, and do a more smart parallel processing in the distributed environment, so that we're able to leverage the best out of every node. Now, on the document store. Now, in the document store, there are various possibilities. We can have data in the form of JSON. We can have data in the form of XML. Even though, I mean, the data is primarily in the form of JSON that you will see in there. Now, in the JSON, there's always a key. There's always a key identifier and the actual data object that actually represents the actual data in there. So the data in there might be primarily a JSON or an XML format. That's how a document data store works. Now in the column store is primarily Cassandra is one of the most smartest column stores in there. Now in there, the data is primarily stored in a bunch of columns as compared to the reverse of rows that we use to store. So I mean, all the columns, they are connected to each other. What we actually identify, how we represent them, a bunch of columns is always represented by the column families, and that column family is always identified, is being uniquely identified by the row key or the partition key. The partition key is always responsible that the partition key is always responsible to preserve the data across multiple nodes within that specific cluster, to ensure that how data and which row or which set of columns will be going on which specific instance is being devised based on the algorithm that partition key specifies. And that's how a column store works. So that's how a column store. So I mean, there's column 1, it will have A, B, C, D, and there's column 2, it will have 1, 2, and 3. So it has only 3 different columns. So that's very important. That's very smart. So I mean, that is what I was trying to say. So I mean, there is a possibility that the columns for different elements might differ. So I mean, it's like it's very similar how exactly how a table behaves in there. However, it's being replaced in here. The problem in there is that if there are 5 different columns within a specific table, so all the rows would have the values, or will have the information for all those columns that are specified in there. However, there's a possibility. However, in case of a column store, column-based data store, just like Cassandra in here, it's primarily does not require to have any value for that, so it will probably be empty or null for those columns that don't exist in there, and the remaining others would continue to have. So that means there might be the column families, there might be set of columns that have only three fields, and there might be another column family who has 10 different fields. So, and they might be, and there's even possible that all those 10 fields might be completely different than the first 3 fields in the first column family. So that's how a column store works. Now, in case of a graph is always based on the nodes and how the relationships actually work, how the relationships are being defined, and then the information, some part of information is being stored. The node is the actual entity, and the nodes will keep on growing. And then the node label actually identifies the kind of information that will be stored, that will be preserved on the specific node. And the information on node can always vary and can always change. So no, the node is actually the information that actually exists in there. The only difference of a graph store as compared to the remaining three stores, the key value, document, and column, is that graph actually stores the ACID principles. It has better transaction management as compared to the remaining other unstructured stores. So you can actually store a lot of transactional stores, transactional data, or the transactional information on a graph store. There are various flavors. We have Neo4j, we have Orient, we have Titan, we have Cassandra graph from DataStax. So there are a lot of possible features that we can exist in there. This is how a relationship looks like. This is the relationship from node one, and it has three different fields in there. There's ID, name, and age, and then there's another field. There's another node that has a relationship. So these are the attributes that are actually being specified in there, and then these are the edges, the relationship. The edges actually specify the information that are linked to those things. That's how a graph database gets represented in here. Now, what are the possible use cases, or what are the possible things of how exactly which stores actually get used more extensively? The key value stores and column stores are primarily used extensively a lot because managing the complexity and the performance wise, it is always very high, and it's always very scalable. And then the least possible expectations is always being expected from a graph. The graph oriented always will not give you the extensive amount of performance like you will expect in a key value store. That's always expected because since it always maintains relationships in there. But yes, obviously, it still has. There's a huge difference between the performance of any graph store as compared to any RDBMS, any relational data store. So, I mean, since considering the use case of Instagram has primarily used column-based store. Instagram actually started with Cassandra. The Cassandra was primarily built at Facebook's. There were a few bunch of people now since the amount of data actually started growing on Facebook, and there were a lot of data deadlocks that actually came in there. So in order to make sure that Facebook has an extensive performance up and running, that's why Cassandra was written. Cassandra was first written on Facebook, then it was actually made open source. It was made available in the open source, and then the Apache community was actually there, who was responsible to enhance, and who has been an effective contributor, and the open source community has been there, and that has been helping us out in optimizing and adding new features to the Cassandra store. Now, if we talk about the performance of any NoSQL store as compared to any RDBMS that we have in there in picture, or if we talk about the NoSQL stores as compared to within them. Now, the operations that we are actually trying to do, I mean, if we scale up, now, as soon as we go up nodes, Cassandra has always been a winner, has always been good at actually managing a high volume of data and extensive performance, especially when it comes to writes. There has not been any other better performer in case of writes when it comes to Cassandra. That's a similar example in here. Now, if we actually grow almost to 32 nodes, 16 or 32 nodes, you can yourself see the difference. You can see how many number of operations will Cassandra be able to perform. It's close to 37 or 38,000, 380,000 writes as well as reads that Cassandra will be able to perform as compared to Mongo. Mongo can primarily perform probably 50 to 55,000 writes, even though Mongo has enhanced a bit as well now with the Mongo 3 in picture. The performance has probably gone up a bit as well as compared to this slide now. Now, Cassandra, since the Cassandra was actually chosen, so the best part about Cassandra is that fault tolerance has always been a very, very key feature of Cassandra. It does not have any single point of failure. The reason for not being a single point of failure is that Cassandra works on the gossip protocol, so it does not have any master-slave concept in there. So there's always an advantage. It always gives a big edge. Now, since there's no specific master in place, so it's always very easy that every node has information of remaining other nodes that are actually there. And the second best part in Cassandra, it's completely free and open source. Anyone can come in and hop in and dig deeper and leverage the best that's available in there. And then the scalability of Cassandra is relatively very easy. You can always add multiple nodes in Cassandra at any point of time, or you can downgrade the nodes at any point of time without actually doing a lot of complex configurations. It's relatively very easy. The configuration, the management and configurations or administering the Cassandra cluster is relatively very easy. And then the data sets or the high volume data, whether we are talking about the reads and writes within Cassandra, it's relatively very fast and very rapid. You will not really see that they won't be taken, because how Cassandra works, actually it breaks off the actual data into smaller chunks and then does the concept, then actually performs the operations on the micro batches. So the amount of processing is always very extensive, and with that it always gives you a very extensive and very high scalable performance in place. And then the reliability in Cassandra store is always very extensive, and it's always, and then the consistency, how Cassandra actually behaves in case of consistency, whether we talk about the consistency within the reads or the writes, is always relatively very easy to perform those operations in there. Now, Cassandra, obviously, certainly, it's one of the most popular NoSQL stores that's there available in the industry as of now. And then the management of Cassandra is relatively very easy. It's primarily free, even though there is an enterprise version of managing and monitoring available with data stacks. But that's something that has been built on top of the basic feature that Cassandra itself provides in. And then the management of data, the high volume of data, and the managing of data, whether that's reads or writes, or the managing of data, that's always very easy within the Cassandra cluster or across multiple servers within the Cassandra environment itself. Then the availability, the possibility of a failure, the fault tolerance, and high availability, the HANFT are always very good with Cassandra, and it's very easy to manage both of those things very smartly and very easily at your convenience. The robustness. Now, since the best part about Cassandra is that we can always, Cassandra is very smart across sharding and data centers. We can always have different data centers working within the same cluster. We can have various servers that are pointing to a single one data center, and then there might be another set of servers that are pointing to another data center. So, I mean, I can give you a realistic example where exactly this makes sense. Some time back, we had an application. I was working for one of our clients. So we have an application, and there was a few of our servers were actually deployed in Virginia, and few of our servers were actually deployed in Singapore. And suddenly, the data center store that actually was actually deployed in Asia had one of the copies, and suddenly one of these servers actually got down. So the challenge was that since it was a sharded, so there was a lot of sharding applications that had been configured. So that means there was a copy of every other server on probably one of the alternate servers. So what we had done is we had kept one copy in one different zone, that was in data center 1 probably in Virginia, and data center 2 in Singapore. So the advantage that it gave us was that we had there was no single point of failure. This was one of the possibilities, because since we don't have everything within one single data center, so the advantage was that the behaviors with respect to how it behaves in Virginia would be different as compared to how it behaves in Singapore. So now that is something that is possible specifically in Cassandra at the data center level, even though we can do it even more granular at the rack level as well. And which rack of that data center is this server actually being deployed? But see, these things, the concept of data centers and the racks, this makes really more sense when we're talking in the cloud environment, because primarily when we have whether that's a public network or a private network, it makes more sense. And it always gives us more advantage of scaling up within a different data center across multiple across a continent or across that's clustered in itself, right? So the advantage in there is that you can have probably the performance of Cassandra is always very good across multiple data centers because it works smartly. It tries to identify which one is the closest one inside that specific circle, and based on that, it tries to send a request to that specific data center, or as compared to going to the most farthest one. This is the basic one. Then, I mean, how exactly the evolution of Cassandra actually happened. First, it was developed at Facebook for the basic search engine, and then it was open source in 2008. Then it went to the Apache's incubation in 2009. Then it went to the Apache Foundation in 2010. Then it became quite popular, and then that's how the ecosystem of the Cassandra actually moved on. But yes, it has been it actually there was a huge impact of, I mean, how Cassandra actually works. The structure of Cassandra is assumed, or it's being influenced, that it was primarily influenced by Google's Bigtable and Amazon's Dynamo. I would say primarily it was Bigtable, because if you see how the Cassandra's architecture works, that's quite similar to how Bigtable works. Even though yes, Cassandra has done some more updations, primarily after its releases, and it has evolved a lot since then. But the basic architecture still remains the same. And then yes, the DynamoDB, obviously yes, the Amazon has done a lot of work in there as well. So that has helped a lot in actually Cassandra's evolution in itself. So now, I mean, if we just have we went through how Cassandra behaves, how it was the evolution, what was the evolution, the big data, how big data evolved, what makes sense in what kind of store, where does it make sense to have a key value store, wherein does it make sense to have a graph store, wherein it makes to have column stores. And then now it's important now then when we moved on to the evolution of Cassandra. So it's very important that we should know that what are the most prominent features of Cassandra itself. The most important feature of Cassandra is its writes. It's very, very consistent in writes. Cassandra is very powerful in writes. And then the high availability and fault tolerance. It's very, very smart in high availability and fault tolerance as well. And then in the consistency, it's always very tunable, and it's always very reflexive in its nature. And then with the introduction of the CQL as compared to the previous thrift, the CQL has been very smart, and it's very easy for anyone to actually perform, especially someone who is actually doing a transition from an RDBMS store. It actually makes your life relatively very simple and very easy. Then the data store, it's always very flexible, because since it's an unstructured store and then it's a column based, so then the number of columns can always scale up or scale down, and the behavior and the amount of data or the kind of data that we can store within those columns can always change. And then the distribution, how the sharding happens, or how the partition of data actually happens across multiple nodes within a specific cluster, can always change as well. The configuration for that is relatively very simple and easy. And then the scalability. Now, since we can have various, since we are actually, there's always a possibility, especially in NoSQL, it's a very common thing. We don't always start from a 10 node cluster. We don't primarily start from a big setup from the first go. We always tend to start from small. We always start a very small cluster, and as soon as the need goes up, as soon as the data coming in actually increases, the velocity increases, the volume increases, the cluster spreads across as well. That's where the scalability is always a key. So it's very important that your system should be able to scale horizontally as well as vertically, right? Yeah, so that is the best part about the scalability. So it's important that we should know that your store should always be able to store horizontally as well as vertically. Even though Cassandra is primarily a horizontal scalable structure wherein you have to keep on adding more nodes to scale it up, and then the cluster itself will be smart enough to actually decide which data will be going on to which node. I mean, yes, we can always do the custom sets of tweakings. So with this scalability structure, it always gives you a very high availability. So there's almost 100% high availability, and there is no downtime that's available in there. And then when it actually scales up, the read and writes, the throughput for read and write increases as well. As soon as it increases up, as soon as the node actually jumps into the cluster, at just that point of time, the amount of reads and writes increases as well. That's a very smart thing, because what Cassandra, since in Cassandra, the best part in Cassandra is there is no concept, there is no master and slave concept. So every other node will be able to interact with every other being that's available in there. So that means, let's suppose that there were only 2 different nodes in picture as of now, but as soon as we scale up, there's if you add 2 more nodes, if they were actually expecting earlier they were expecting only 10, now they will be able to perform 20 or 30 or, because the amount of node actually gets distributed across, the amount of load actually gets distributed across multiple nodes in there. Then in the distribution, now the distribution is since the best part is that since there's no master slave concept, so the distribution is relatively very easy. There is no master in there who actually decides, who makes a decision to understand, to ensure that which data will be going to which specific node. So since it's a peer-to-peer, so it's a gossip protocol. So as soon as the node actually comes in here, you get some data. If node 1 feels it okay, he says he has actually enough data, he goes and he keeps on sending the remaining other data, actually goes on to the node 2 without actually intervention of any other nodes. So they are smart detectors. That's what I call them. That is, they are smart, and every node is so smart enough to make their own decisions. So that makes the performance of Cassandra very high and very extensive, especially in a distributed environment. So the flexibility of distributing data is always very good. So it always helps us off in there. Now then, the high availability. Now, since the data that actually is actually being stored at one store, and let's suppose that when we are working in a clustered environment, so there is always a copy of that data that's actually being replicated on any other alternate node that might be within the same data center or across data center. That depends on the configurations, or if we have done any tweakings, or if we have done any changes as well. And then in case of writes, Cassandra is very effective in writes, since Cassandra stores a huge amount of extensive amount of writes. It's very smart in making writes, since it works on a 2-phase commit. So there's always a temp store wherein, and then there's a concept of batches wherein Cassandra keeps on going and writes, keeps on making the writes from in those batches based on that. And then the CQL. The CQL was effectively introduced. It was upgraded from Thrift. Cassandra moved ahead from the Thrift itself, and CQL is primarily very similar to any RDBMS structure query language. So it makes relatively simple transition for people who are coming in from an RDBM relational database store. And the flexible data store, the best part is that's always a good advantage of any unstructured store. Whether you want to store the data in a structured format, you want to store data in unstructured format, except for the relationships, the possibility of what kind of formats you want to store and what kind of data do you want to store, and there's a possibility that you might actually change the structures that you are actually storing in there. So all these possibilities, all these flavors, the behavior of the response of Cassandra to these changes and these transitions is very, very smart, and it's very, very convenient to do those transitions or to do those changes. And then the consistency. Consistency is primarily to ensure, I mean, how consistent it actually performs the writes, or how consistency it performs the reads. So that actually depends. I mean, that is primarily, I mean, let's suppose that whether we actually want to go more on the availability side or on the consistency side. So now, as I told you, now that actually primarily depends on how we are actually trying to behave, right? Now, writing on making sure whether it's consistent or the availability. So that primarily depends on how exactly how the consistency actually works in. Now that's what the CAP theorem actually primarily states on. So now see, that's what I was trying to. Now primarily every NoSQL behaves or responds to only two of the possible structures at once. It can be either consistent and available, or it can be consistent and partition, or it can be available and partition, right? Now, based on different NoSQL stores, they respond differently to to all three of these. So, I mean, it depends on the behavior of that NoSQL store, just like the big table, the HPS, Mongo, or Redis, they primarily work majorly on the consistency and partitioning. Then the DynamoDB or CouchDB, they primarily work on the availability and partitioning. And the RDBMS, they primarily work on the consistency and availability. They are not much on the partitioning side. So it depends. Now, the consistency is actually when I say, I mean, what exactly consistency means. Consistency is primarily, I mean, what is the return, what is the most recent value that was actually being written, whether that is in process or that's actually being written. And then to ensure that the most recent write is actually being returned across all the nodes. So that means it might be that even if that node or that data is actually being just written, or it's still in that process. So I mean, to make sure that there's consistency across all the nodes, that's very, very important. Then the availability, to ensure that, okay, if the performance is actually being, to ensure that the cluster, the system is available 24/7, and all the operations are being handled properly. It's very very necessary that everything is actually being responded successfully without any failure. That is what the availability talks about. And then the partitioning on tolerance, right? So to ensure that, let's suppose now, since the partitioning, since primarily the basic concept of every NoSQL is to manage high volume data, big data. And so big data is not majorly deployed on one single node. We always have a bunch of nodes, a cluster in itself and all together. So now since the data is actually being spread across multiple nodes in there, so it's always possible that a copy of one node, one node might not have all the data, and that it might have only a chunk of that data, and the remaining chunk of that data might be available on the remaining other nodes. So that means, let's suppose if there are 10 different records, and there are three different nodes, there's node 1, node 2, and 3. So there's a possibility that node might contain 4 records, and node 2 and node 3 might contain the remaining 6 records. Now somehow, let's suppose that node 3 actually got down. So to make sure that even in case of errors, we ought to make sure that we are still available, we are still able to handle that failure, and the data that was actually partitioned to node 2 and node 3, we don't lose that data. That is what the partitioning actually talks about in case of failure or in case of tolerance. Now these are the various possible these are the major possible things wherein Cassandra is actually being primarily used in. So I mean, in Spotify is primarily for availability in the product catalog, primarily for the high availability across, since it works across multiple data centers. Then the Eventbrite is mainly on the read and write capacity, because it works on high availability of read and write. And the NREL, it's primarily on the high volume, since the volume of data that Cassandra can perform on can always be very high and very good. So that's always a very good thing. And then Comcast is again on high availability. And then Simility, it's again on defensive measures to ensure that the security managements, I mean, managing security in Cassandra is relatively very easy. So there are various things that you can do to ensure that you don't actually lose data that easily, or there's no data compromised at any point of time. There are a lot of companies who have been using Cassandra. Is honestly the most popular NoSQL storage. A lot of big companies actually prefer it, and it makes sense as well. And especially in the recent times, as we have actually gone up, as the data is actually moving up, so a lot of people are actually preferring to choose data. These are some. These have been some problems that Netflix have actually faced, because Netflix actually uses a lot of Cassandra storage. So I mean, there were a few issues that actually Netflix has faced earlier. Now that's where exactly that's the reason why Netflix actually went on with Cassandra to overcome those challenges, especially with the consistency, the data integrity, and the more optimum ways of actually restoring and backing up its data stores at any point of time very smartly. And then it's the best part is Cassandra is cheap. It's almost for free, because since there is no specific there's no specific cost that actually that is being incurred by Cassandra other than the installation cost. So it's always very easy, and the scalability of Cassandra is very easy, and it's very convenient. We can always scale up, and the best part is across multiple regions. We can have a single cluster. We can have a multi-region cluster supported in Cassandra. Not many NoSQL stores provide that kind of configuration, and that actually makes a smart thing, because that reduces actually the possibility of failures. The fault tolerance and the high availability actually make a lot of sense in here. Netflix is actually being using Cassandra extensively. The number of clusters that they actually have deployed in production is large. It's almost 30 odd clusters. And then how many regions they're actually spread across almost 12 multi-region clusters, and every region at least has three clusters, and the terabytes of data that's across clusters is almost 65 terabytes, and there are almost 470 odd nodes. So that's a huge amount of data, and the most interesting part in this is the number of writes that are actually being made. The number of writes is primarily more than number of reads. So there's almost 250,000 writes that Cassandra is making. As I told you earlier as well, that Cassandra is more stronger on writes than on reads. So when we have higher amounts of writes as compared to reads, that's where Cassandra makes more sense. I mean, yes, certainly I don't say that the reads are not that extensive, but Cassandra gives 100% guarantee on missing a write, and that is a big thing, because see, reading data is not that challenging. Yes, the performance makes sense, but losing the data that actually is coming into your store is always very difficult. If you lose a single packet of data, that means that can have a huge amount of impact. You don't necessarily know that how and when you will be utilizing that data, unless you exactly know the kind of structure. And because we don't know, we might be actually getting that data input from some any other external source or a third party source, and we might not get that data again. So it's important that we don't really lose those data stores at any point of time. This is Netflix's architecture, how Netflix is actually being used. So there is a specific memcache that actually be that's what I was talking about. This is the intermediate layer for the integration for Cassandra, for actually storing with an in-memory store, or a temp store is relatively very easy. Well, that's all for the basic introduction and the basic features that we have in Cassandra, what all things and why Cassandra makes sense. Now, I will try to walk you through, in the remaining part of the session, I will try to walk you through on the installation of the virtual machine. As I told you earlier, that for your convenience and for your ease, we've ensured that we have set up all the softwares in a single virtual machine. You just need to download that virtual machine and use the same image copy in your any of the virtual boxes, and you are good to go. Okay, so this is the installation guide. So I mean, you might actually be required that the virtual machines that you'll actually be that will be supposed that we are supposed to install. So I will explain you the expectations. I will explain to you what are the basic steps that are required to do the installations and to perform these the basic levels of operations and the guidelines that we need to keep in mind while we're actually doing the installations. But before that, I would like to have an overview of a brief summary on compiling up what we learned today. What is big data? So I mean, the data, a high volume of data that is structured, that's unstructured, or that's semi-structured. That is what primarily comprises of big data. And then the possible available stores. I mean, one of the most problems, the possible things, the limitations of RDBMS, wherein RDBMS is not really able to suffice the high volumes of data, and it's not able to primarily manage high volumes of data. That's why a new thing came in picture, a new terminology of which is NoSQL, wherein we have a lot of these, a bunch of important new features. Because see, now right now it's primarily more on the data side than on the application side. Now, since a lot of systems have already been placed, they're already being set up, so now the most important part is that our application is strong enough, and then the application data that we have in place, we are able to manage that data. And the since with the number of users adding up to the existing systems that we have in place, and that always piles up to the existing velocity as well. So that's why that's where the evolution of NoSQL came in picture. And certainly we have various flavors of NoSQL. We have Aerospike, we have MongoDB, we have Elasticsearch, we have Cassandra, we have graph databases, we have DynamoDB, we have Couch, Redis, React, so on and so go. It's a pretty long chain. And then, I mean, Cassandra is certainly a document, is primarily a column-based data store, wherein the data is majorly stored in the form of columns, and the bunch of columns are always referred to as column families. And then a major advantages of Cassandra is its high availability and durability, the scalability of Cassandra stored within a specific cluster, and that cluster can always expand itself to one or multiple regions simultaneously at same point of time. Cassandra behaves smartly in case of across various data centers. It always has a very effective way of performing the writes. And then in case of consistency and durability, Cassandra behaves very smartly. Then when we talk about the CAP theorem, the most important theorem, when we primarily talk in case of NoSQL, Cassandra is primarily more on the consistency as compared on the availability. So it's very important that no single store, no NoSQL store will be able to give all the three features at the same point of time. So it's always a trade-off between consistency and availability. So that means if there is a data store, if there's a data store cluster of probably three different nodes, and probably there were two different writes that actually came in the same place, and there was a read request one of the nodes at the same point of time, let's suppose, and suddenly whilst these three operations were being performed by these three different nodes, two of the nodes got down. So now the responsibility of that one node is to ensure that how it actually will perform, how it will be able to make that right, how it will be able to make a decision between to give a consistency in the writes, or to make sure that the availability is being ensured. So that means to make sure that do we need to lose those writes, or do we need to make sure that the data that's already available in there, that needs to be responded back smartly. So it depends, even though, I mean, that depends. So we can always do a lot of tweakings, and we can always do a lot of configuration setups that are required to make those decisions behave the way we want them. Yeah, for future references, there are few tutorials and few useful links that you can always refer to. And there are few standard questions, standard Q&As for the basic based on today's topic that we have deployed in here. So probably you can refer to this link and probably just have look at your knowledge, what you have learned till now. That's primarily what we have in place. Now for installation, there is the first thing that you require is to download the VirtualBox. For downloading the VirtualBox, you can refer to this document that's mentioned in here. And for that, you can go to this specific URL and you can choose whichever actually applies to you, whether if you're using the Windows one, if you're working on Windows, you can download the Windows installer. If you have Mac, you can download the DMG, or if you're working on any of the Linux platforms, you can choose whichever DBM app applies to you. It's a 32 GB or a 32-bit or the 64 bits. Based on that, once you actually have downloaded the VirtualBox, then the installation actually specifies. The installation guide is relatively simple. It's a very easy guide. This is actually the same URL that I just pointed out to. Once you have this downloaded, you can follow up the wizard to do the installations. And as soon as you go up, you can change the location on which you actually want to install. This location, this is primarily the look and feel of the Windows installation. So the whichever one actually applies to you, you can choose whichever one. But primarily the look and feel of the installer would be relatively similar across multiple platforms. Once you have the installation complete, this is the look and feel window that will be actually defined to you, that will be available to you. And as soon as you do the installation, it will ask you for going on. You can choose now. The next step that you really require is go and download the Cassandra's VM that Edureka has created. You can click on the link that's actually been specified. And as soon as you click on the download link, it will download the corresponding virtual machine for Cassandra that's required in there. Once you have downloaded the corresponding virtual image in there, then you can go to import alliance. And as soon as you go to import alliance, you can add that in here. It'll ask you, you can point the application to that specific location for that file. You can use the same wizard in there. Once you have added, then you can add the specific configurations that are required in there with respect to the network and stuff. Once you have specified in there, then you can start the corresponding VirtualBox in here. Be sure, yeah. So this is my VirtualBox. This is the installed one that I have just installed. So now, if you click on start, it should start the Cassandra's VM. So it's going into the installation mode. It's going into the startup mode now. It will load the Cassandra. This has a CentOS within itself. This is Linux's VirtualBox machine, so it will load the Linux server for you. Cassandra is already pre-installed on this. So as soon as it loads up, it will pop in with this login window that for the Edureka user, wherein the password is Edureka as well. See, it's yet to start. Let's go back here. As soon as you log in here, you will be able to land on to the desktop screen for your VirtualBox. So that means you first need to install the VirtualBox. You need to download it. You need to install it. Once you have installed it, then you can specify. Let me log in Edureka. Once I log in, the desktop for my virtual machine will be displayed. And people who are already familiar with CentOS, I'm sure it will be primarily easy. It won't be that complicated for them. Yeah, so I've logged in to the screen. Now for actually going in and traversing through the remaining set of features in there, we can go into terminal. Go into terminal. Let's see. CQLSH is the shell command for loading in the CQL. Now, since Cassandra is not started, so we go and we start the Cassandra in here using the Cassandra command. So it will start the Cassandra for us. And as soon as the Cassandra is started, let the Cassandra start. As soon as the Cassandra is started, we can load the CQLSH. Start the CQL. So we're logged into the CQL cluster. Now if we log into the CQL cluster, so we are already logged into the CQL cluster now. Okay, let's close that for now. Now, as soon as it actually logged in, now since there's only one single node, that's why it actually shows you the nodes, the name of the node, the URL in here, and it shows up. Now, since by default, Cassandra works on the ring topology, on the gossip protocol, so all the nodes that are actually available in there in that ring, it will try to link, it will try to interact, or it will try to connect to all of the nodes that are available in there. But since there's only one single node in there, that's why it finished joining. But it tries to search it off. It tries to find out if there are any nodes in there. These are the set of tokens that actually are already specified, or that are already defined in there. So these are the tokens based on which the partition keys actually get created for those column families that we have specified. And then it shows you, the other thing that it actually shows you in here is what is the information about the Cassandra, and what is the information about the others, the other related information that we are supposed to understand. Cassandra's version in here is 3.1, 3.11.1, and the thrift is 20.1. Thrift is actually the top level protocol that is being used, that Cassandra uses for the external communications. Thrift is a protocol in itself, and it in order to use that protocol, Cassandra makes use of the Thrift API. The SQL works on top of that. SQL is primarily to give you a more user-friendly, and so SQL Cassandra, this Cassandra package bundles in with the SQL as well in here, and the SQL version for this is 3.4. Now, since by default this works on the native protocol, that's why it actually loads the basic protocol in here. By default, it tries to load all the column families that are available in there, that are pre-available in there. So since we have not created any column family, that's something we will be doing in the next upcoming sessions. But as of now, it loads all the existing column families that we just saw in the key, that we just went through previous terminal that I just closed off when we had actually tried to log in. And then these are the JVM arguments that Cassandra actually loads in. So there are a lot of, since it actually does a lot of work within in memory, so it's very important that we actually allocate a huge bunch of a big chunk of the in memory in there, so that Cassandra is actually able to perform any levels of operations that are required in there. Because while actually I told you that Cassandra actually performs two-phase commits, so Cassandra doesn't actually really go and write into the data stores in one single go. It actually makes a write in there in the first, and then based on that, it actually starts writing data first into a temp file, into log, and then those log files are actually being moved on to the actual permanent stores. That is how the big table used to work, and that's similar. That's very similar. That's very identical. How that's what Cassandra has adapted from big table, and that's how Cassandra actually tries to work. Cassandra has a configuration file, cassandra.yaml, and that actually has the list of all the files that are actually being created in here. Okay, let's close this off. So now closing the instance back off, you can power off the machine. You can close this instance off. You can close the VirtualBox off. Now, there are a few settings that you might require primarily for the network ones. In case you might want to choose whichever network is applicable to you. Based on that, you can actually specify whether it's a bridge adapter, in case which one is the bridge adapter that you are actually using, or if you're using a NAT network, then you might actually have to specify it. Since I don't have any NAT networks available in here, that's why it doesn't actually tell me to specify in here, because by default, a lot of times what happens, primarily if you are using Linux environment, so the network is majorly disabled on the virtual boxes in the Oracle one. So you won't be able to access internet in there on your virtual boxes. So you might have to explicitly configure that on your own. For that, you will have to go in there in the settings. That's what those settings are all about. Then there are a few more settings that you can actually specify in there. Even though, I mean, audio is not required in your case, it's primarily the ports and networks that you might require if you want to copy any stuff in there. Then you have the shared folders. I mean, if you actually want to share anything from your local machine to the virtual box, that's what that shared folder is actually about. The shared folder actually takes care of that information in there. That's all for today. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!